You know, every time you make a call, send an email, or stream a video, your data is zipping through this huge hidden world of networks. And it turns out, the whole thing basically runs on one of two fundamental ideas. So today, we're going to pull back the curtain on this epic battle for bandwidth: circuit switching versus packet switching.
So here's our game plan. We're going to start with the classic idea of a dedicated line, then see how you can slice it up and share it. After that, we'll meet its more modern, flexible rival. We'll even run the numbers, put them head to head, and finally, figure out which one really powers the world we live in.
All right, let's dive right in and start at the very beginning, with the original solution that was actually born from the first telephone networks.
And that's really the perfect place to start, because the simple act of picking up one of those old-school rotary phones, it perfectly captures the spirit of our first big concept. And that concept is called circuit switching. The idea is, before you can even say hello, the network has to build a fixed, dedicated connection just for your call. It reserves everything needed, the transmission rate, the buffer space, all the way from your phone to the other.
The best way to think about it is like a fancy restaurant that only takes reservations. You have to call ahead, you go through that setup process, but when you show up, your table is guaranteed. It's waiting for you, and you get seated immediately. Your service is guaranteed.
And check this out. This visual just nails the idea. See that clear, unbroken blue line connecting the two computers? For their entire conversation, that path belongs to them and them alone. No one else can use it. So this begs a pretty big question, right? How can you have thousands, even millions, of these private, dedicated circuits all running over the same physical fiber optic cable? Well, the network has a couple of really clever ways to slice and dice that link.
Okay, the first method is called frequency division multiplexing, or FDM for short. This is where the link's entire frequency spectrum gets divided up into different channels, and each connection gets its own private frequency band to use.
It is exactly like FM radio. You've got all these stations, 93.1, 107.5, you name it, and they each have their own unique frequency. They're all traveling through the same air at the same time, but because they stay in their own lane, they don't mess with each other.
Now, the second method is time division multiplexing, or TDM. So instead of slicing up frequency, TDM slices up time. It divides time into these little repeating frames, splits each frame into a bunch of slots, and then gives your connection one specific time slot in every single frame that goes by. Picture a really structured round table meeting. Person 1 gets exactly 10 seconds to talk. Then person 2 gets their 10 seconds, and so on around and around the table. And here's the key. Even if you have nothing to say, your 10-second slot is still yours, and everyone has to wait for your turn to pass. That's TDM. But here's the big problem with all of this. A voice call is a constant stream of sound, right? But most of the data we use today just isn't like that. It's bursty. Think about it. You click a link, you get a quick burst of data for the web page, and then nothing while you read. That whole time, your reserved circuit is just sitting there, completely empty. And that massive inefficiency led to a totally different idea.
And this is where packet switching enters the scene. Instead of building a whole dedicated circuit, your data, say an email or part of a website, gets chopped up into these little blocks called packets. Each packet is then just tossed into the network on its own, and it finds its way, using resources as they become available.
So let's go back to our restaurant analogy. Packet switching is like a super popular taco stand that doesn't take reservations. You don't have to call ahead, you just show up when you're hungry. It's way more efficient and flexible. But hey, if it's the lunch rush, you might have to wait in line for a few minutes.
Okay, this is where it gets really interesting. Let's actually pit these two approaches against each other with a real-world example. Because the numbers, they tell a really compelling story about efficiency.
Okay, so here's our setup. We've got a single 1 megabit per second link. Each person using this link needs 100 kilobits per second, but only when they're actually active. And here's the kicker. They're only active about 10% of the time. The other 90%, they're just idle.
So first up, let's look at circuit switching. Remember, you have to reserve a full 100 kilobits for each user, no matter if they're active or not. So the math is dead simple. 1 megabit divided by 100 kilobits, that means the link can support exactly 10 users, period.
Now, just let that sink in for a second. Because those users are only active 10% of the time, it means that for 90% of the time, those reserved, dedicated circuits are sitting completely empty, wasting all that capacity. It's like booking 10 tables at a restaurant for the whole night, knowing 9 of them will be empty most of the time.
Okay, now for packet switching.
Using the exact same 1 Mbps link, you can support 35 users. No, that's not a typo. 35. That's more than 3 times as many people. So, how is that even possible?
It's basically the magic of statistics. The network is making a bet. It's betting that it's just incredibly unlikely that more than 10 of those 35 users will try to send data at the exact same instant. And the odds of that happening are just a tiny, tiny fraction of a percent. The rest of the time, there's plenty of bandwidth to go around for everyone.
So as you can see, each approach comes with some pretty fundamental trade-offs. It's not as simple as one being better than the other. So let's lay them out side by side and really compare.
This table really sums it all up, doesn't it? Circuit switching reserves everything up front. That makes it inefficient for that bursty web traffic, but it gives you a constant, predictable delay. If the network's full, you just get a busy signal. Packet switching, on the other hand, shares everything on demand. It's super efficient, but it means your delay can be all over the place. And if it gets too busy, your packets have to wait in line, in queues.
So let's bring it all home and see how this all comes together to build the actual internet we use every single day. I mean, based on our little showdown, it seems like a total knockout for packet switching, right? More users, way more efficient. It seems like a no-brainer. But the real story, as always, is a little more complicated than that. The answer is no, not always. Think about something like a video conference call or a fast-paced online game. That variable, unpredictable delay you get with packet switching, it's a killer. It causes all that stuttering and lag. For those kinds of real-time things, you absolutely need a guaranteed quality of service.
So here's the bottom line, the real takeaway. It is a fundamental trade-off between guaranteed, predictable performance versus on-demand, flexible efficiency. The internet we all use is built on the incredible efficiency of packet switching. But engineers have come up with some really clever tricks and protocols to basically create circuit-like guarantees on top of it for those moments when we really, really need them.
So, we've just settled the battle for a single connection. But how do you scale that idea up to connect billions of devices across the entire globe into one seamless web? Well, that's where we're going next. Join us for our next explainer when we dive into the amazing network of networks.